So you should have watched this YouTube link. Don't stress if some of the concepts went over your head. That is completely fine. We're going to unpack these ideas about the dilation of time, so time slowing down relative to an observer, and length contraction, things actually contracting in length as they're moving at relativistic speeds. So if I ever say relativistic speeds, I mean speeds close to the speed of light, and that the speed of light is a constant. We're going to unpack all these ideas individually. So in this video, we're just going to look at the following. You need to know that motion can only be measured relative to an observer. Okay? Length and time are relative quantities that depend on the observer's frame of reference. And we'll look at this over some slides. Now, we need to know that observations of objects that are travelling at very high speeds, they cannot be explained by Newtonian physics, or the equations of motion stuff that you've been looking at. And Einstein's theory of special relativity predicts different results to those of Newtonian physics for velocities approaching the speed of light. So this Einstein's theory of special relativity is based on two postulates, or two assumptions, and they are that the speed of light in a vacuum is an absolute constant. Okay, speed of light in a vacuum is a constant, and the laws of physics are the same in all inertial reference frames. And we'll unpack all these new these new words, this key vocabulary over the next few slides. So first thing is a reference frame, or a frame of reference. And it's basically just a set of coordinates in which we can define some sort of position. Okay? In most cases using just the normal Cartesian coordinates, x and y. So, you know, it's important if your displacement is positive or negative, etc. Now, whether or not you are moving depends to your frame of reference. So what we're going to do is we're going to look inside this box. So if you're inside a moving, imagine this is just a train carriage, for instance. If you're inside the train carriage, so you're the woman in red, okay? You, from your frame of reference, you're standing still, you're stationary, okay? You're at rest. However, if you are being observed from a frame of reference that is outside the train carriage, okay? Now this lady, she's actually moving. She would be moving to the left if it was you could see through a window. So your relative motion is depending on the frame of reference from which you're being observed. So this woman inside, she's stationary, okay? Someone observing her that is on the ground is watching her move to the left. So she's actually moving. So they're frames of reference. Now, an inertial frame of reference is one in which Newton's laws of motion apply. So Newton's three laws of motion, they apply only if an object is stationary or moving with constant velocity. So an inertial reference frame is therefore either a stationary reference frame or a reference frame whereby something is moving with a constant velocity. So someone outside observing this yellow person, if they were stationary, they are at an inertial reference frame. And if the person inside the train carriage, if the train was going at a constant velocity or a constant speed to the left, then this woman would also have an inertial reference frame. And thereby, the Newton's laws of motion will apply. So we've gone through reference frames, and in particular, inertial reference frames. Now, this is a thought experiment that Galileo did. Now, if Galileo climbed up to the crow's nest, or whatever you want to call it, the nest on top of a ship, and were to drop a ball, from Galileo's perspective, it looks like it's just falling straight down. But if you're a bystander on land and you're looking out towards the ship, because the boat is moving, when they drop the ball, the ball is gonna look like it's following a curved path. Okay, so from the bystander's perspective, the ball looks like it's following a curved path. Which observation is correct? The straight down one, or the curved path that the person on shore that is stationary is observing? Just have a think to yourself, which one's correct? They're both completely correct because motion is relative, okay? You can observe the same event in completely different ways based on your frame of reference. So, relativity, all the calculations that we do in the first three topics are almost separate to relativity. We're not going to consider the frame of reference in any of the first three topics, but we are now going to think about that motion really is relative. And the next slide will make more sense of that. Okay, velocity is a really good one to think of, that motion is relative. So imagine this person here is on a train carriage. Now, so let's say the train is approximately moving at 10, or it is moving at 10 meters a second to the right. Okay? Now, this person, from their frame of reference, they're stationary. If we were observing the train's traveling at 10 meters per second. Now, let's say this person threw a ball at a constant speed of 5 meters per second. Now, they're going to observe the ball moving away from them at 5 meters per second. However, if there was a stationary observer on the ground observing them throw the ball, this ball is actually going to be traveling at 15 meters per second. The 10 meters per second because of the train carriage, plus the 5 meters per second that the ball was thrown at. So from a stationary observer, this ball would be moving at 5 meters per second. This is just another example of this relative motion, where motion is relative to an observer. So there's a few people, we've got a train, it's moving at 50 meters per second, there's a robber, we've got a couple of security guards or policemen. No, sorry, these are the robbers as well. So this one is on the carriage, so they're on the train. This one is on a stationary sort of platform. Both the bullets are traveling at 100 meters per second. Now, if you were stationary watching this train robbery, so you were on the ground watching this train whiz past, then the bullet from robber A would actually, and if you used a speed gun, okay, which shot out a laser and came back, and you measured the speed of this bullet, relative to someone on the ground that's stationary, this bullet will be traveling at 50 meters per second plus the 100 meters per second that it's shot at. So you would actually measure the speed to be 150 meters per second. However, because this bullet is shot from this robber when he was stationary, you're only going to observe this bullet at 100 meters per second. Now, this person with the bag of cash, okay, would see bullet A at 100 meters per second. However, if he was measuring with a speed gun this bullet, it would only be traveling at 50 meters per second because the train's already traveling at 50 meters per second. So it would be 100 take the 50. So this bullet would only be traveling at 50 meters per second relative to this guy with the bag of cash. So you need to know that motion is relative and the speed of the bullet is relative to the speed of the observer. So if the observer is already moving, it's going to be the difference. Now, basically, so this was Galileo's idea that motion was relative, and it is. However, there was some issues with his model. Now, imagine you had a motorcycle that's traveling at some speed, okay? And then we turned on the lights on the motorcycle. Based on relative motion, the speed of light of this headlight should be the speed of the motorcycle plus the speed of light, which is c, 3 times 10 to the 8. But what happened is that when people measured the light, so a stationary observer measured the light, it didn't travel at the speed of light plus the speed of something, it just measured at the speed of light, okay? So light arrives at the observer at velocity c, not the speed of the motorcycle plus the speed of light. This is basically explaining the same thing. So c is just the speed of light. So perhaps unrealistic. We had this car traveling at 0.8 times the speed of light, so 80% of the speed of light. And then the ball was thrown at 40% of the speed of light, 0.4. So this should be 1.2 times the speed of light. However, from experiments, the speed of light, no matter what, no matter how you were relative to the light, it always measured constant, always measured at 3 times 10 to the 8 meters per second. So we could not use Newtonian physics okay, which is just all the normal motion stuff that you've been doing, we could not use this to explain the speed, explain objects when they're traveling at super high speeds. So light broke this idea of relative motion. So Einstein came up with his theory of special relativity, and the two key postulates or assumptions that he made was that the speed of light in a vacuum was an absolute constant. Speed of light, no matter where the observer was, whether they were stationary, whether they were moving, speed of light was always a constant of 3 times 10 to the 8 meters per second. And his other postulate was that the laws of physics, okay, the laws of physics, Newton's laws of physics, all our motion stuff that we've been learning about, there are the same in all inertial reference frames, okay, which are inertial reference frames, remember, are either stationary or constant velocity. So that's where I'm going to leave you on this video. I now want you to have a go at questions 1 to 4 in the Essentials textbook.